Welcome to a read along with Dr. Powell in the book Discrete Perspectives in Mathematics. This is section 2.2, linking power sets and logic. In section 2.1, we talked about power sets. Now, in section 2.2, we're going to talk about how thinking about logic is a lot like thinking about power sets. Okay, so we need to be able to think about this in the following way. Logic statements or propositions are, how can we think of them as subsets of a set? And they need to be, so they must be subsets of something. So that's what we're going to do. We're going to think about that. So here's some examples of different statements that could either be true or false. Johnny is wearing a red shirt. That's either true or false. Or Johnny is wearing blue socks. Johnny is wearing a hat. Okay, so let's assume that all the statements talk about the same Johnny. And and let's just kind of think about different different possibilities of statements that we could make based upon A, B, or C. We could say something like A or B. Johnny's wearing a red shirt, or Johnny's wearing blue socks. That statement could be true or false, depending on whether statement A was true or false, or B true or false. Similarly, we could do things like this. We could say B and C, meaning that this blue sentence is happening and this green sentence is happening, and that's going to be true if both of them are true, and so forth. We could kind of play with them a little bit. All right, so kind of what we have is we have every statement that we could make based off of A, B, or C depends on the truth or falsity of A, truth or falsity of B, truth or falsity of C. And in fact, some options for A being true, B or C, or however we want like that, will determine whether or not one of those statements are true or false. So for instance, we could have something like this. Let's suppose A is true, B is false, C is true. All right, now if A is true, B is false, and C is true, then let's look at the statement A, let's see, A or B. Well, yes, one of those is true because A is true, say, okay? That would work. So this would be a possible code, if you will, and even think of it as a DNA sequence where you have A, B, and C, and then you have like TFT. So this is a particular code sequence that enables the statement A or B to be true. In particular, let's look at all codes that actually let the statement just A itself be true. Well, that's actually simply all codes that have T for A, right? Likewise, not A, the statement, would be all codes that have F at the first. Not A and C would be all the ones that don't have A, but have C being true, and so forth. What we're doing is we're looking at subsets of possible codes for A, B, and C. And what we're doing is we're taking statements and we're letting them be equal to subsets of those codes. In fact, this is precisely the way that we think about linking logic with power sets. So we're turning every statement into a set. All right. These guys right here, if you want, you could call them atoms. It's a sequence of T's and F's indexed by the collection of propositions itself. Okay. And so, and we include, or we say that a statement has a particular atom in its collection if that atom is something that would actually, if that atom were true, would actually cause that statement to be true. Okay. So, all right. Okay, so you can even say this: a statement is true if and only if the truth is in it. So I mean, an atom is kind of like, so it's a truth false sequence, but you can say, well, is this really the state that things are in? It's a possibility. Like, what if A were true, B were false, and C were true, or something like that? If that were true, then maybe this other statement would be true or false or something like that. So um, so if a statement, which is a collection of atoms, has one of its atoms, and one of its atoms actually ends up being the true atom, the atom that actually represents the situation at hand, then that means that this statement must be true. So a statement is true exactly when the truth is in it. Okay, or the true atom is in, you could say. All right. All right. So kind of what we're looking at is we take the set of atoms, those truth false sequences, and we take the power set of that collection. And that represents all the logical statements that that we're going to be concerned with that are based upon the initial collection of statements. So ways of combining them logically. Okay. So now and there's some conditions which I'll let you look at in the reading itself, but let's go to the next little subsection as well. Okay, so let's think about if one subset or one statement. So you can think of statements as subsets of the collection of atoms. You can also think of them as logical statements, but we're going to be thinking of them in the same way. Notice we use, for sets, we use this notation, subset of. And for logical statements, we use this notation to mean this implies this. Well, we have exactly that P implies Q if P, thought of as a set of atoms, is a subset of Q, thought of as a subset of atoms. The two are equivalent, just as we were implying in the last section in 2.1 in the book. Okay, so in particular, this statement says if P is true, then Q is true. That's the same thing as saying if P contains the true atom, then Q would contain the true atom, which would be, of course, because P is a subcollection of Q, or a subset of Q. And so one atom would go to the next. So we've kind of said P is true exactly when it contains something. Well, if Q contains P is a subset, then of course it contains whatever P does if P is true. So hence it works really nicely and well. Okay, so that concludes this first little read along video in section 2.2. Thanks for watching.